Hi, in this lecture, we'll talk about the finite element formulation of the Navier-Stokes equations and specifically the coupled UP approach. So broadly, there are two classes of methods for doing CFD simulations and solving Navier-Stokes equations with the finite element method. The first approach is the coupled UP method, where velocity and pressure are solved in a coupled fashion. So this is similar to how we did the Stokes equations in the last lectures. And the second approach, which we'll talk about in next lecture, is the fractional steps method, where we solve for velocity and pressure in sequential steps. So today we'll be talking about the coupled UP approach. So we'll start with the strong form of the Navier-Stokes equation. So here we're considering the steady Navier-Stokes equations. For the unsteady part, we can treat the unsteady aspect as we discussed previously with finite difference. So we have the nonlinear convection term, we have divergence of sigma, and we have the body force and the stress made up of pressure and viscous stress parts. We have conservation of mass, and we have a constitutive equation for the viscous stress tensor written in terms of the strain rate tensor. And then we have the domain omega. We can define an inlet boundary condition, which we prescribe velocity. So that's our inlet, Dirichlet boundary condition. On the wall, we have the no slip condition. So that's also a Dirichlet boundary condition. And then on the outlets, we typically impose Newman boundary conditions. So some form of traction, as we discussed previously. And typically, zero traction is a common choice for outlet boundary conditions if you have only a single outlet. Or if you don't know the ratio of flow splits if you have bifurcating outlets. And the zero traction would really mean that your pressure is balancing your normal viscous stresses on the outlet face. Okay, so similar to the Stokes equation, we're solving for four unknowns, the three components of the velocity vector, pressure, which is a scalar, and corresponding to each of these, we have our haste or weight functions. So W, which is also a vector, is the weight function corresponding to velocity. Q, which is a scalar similar to pressure, is a weight function corresponding to pressure. Now, our weak form, we start with the Galerkian formulation, and then we're going to talk about stabilization later. So to derive the weak form, it's very similar to how we did the Stokes equation. So we take the equation, multiply both sides by W. So this is the weight function multiplied by the convective acceleration, the force term. And then we also have the weight function multiplied by the divergence of sigma term, the divergence of stress, which becomes grad P and divergence of tau, the viscous part of stress. And then we also have the continuity equation. And for continuity equation, it's a scalar equation. So we multiply it by Q, the weight function for pressure, and we know that pressure is associated with continuity. So here we have Q multiplied by divergence of U. So all these integrals should be scalar at the end. So divergence of U scalar, Q scalar. And then for the momentum equation, this is dot product between a vector equation and a vector. W, the weight function, is also a vector. So that also gives you a scalar. So really, you're multiplying momentum by W, the weight function corresponding to velocity, and you're multiplying your continuity by Q, the weight function corresponding to pressure. Now, the interesting thing here is that since Q and W are arbitrary, remember, we just arbitrarily multiplied both sides of the equation and integrated, right? So since they're arbitrary, we can add them and form a single equation. So if I have this single equation for both momentum and continuity, since W and Q are arbitrary, it implies that each part has to be equal to zero. So both divergence-free condition and the momentum equation, okay? And as I mentioned, all of these terms, all these integrals give you scalars at the end. So now we do integration by parts, and we do it on the stress and the divergence of sigma term. So for the convection, the nonlinear convection term, and the force term, we keep it as it is. So for the stress term, we perform integration by parts. So this is exactly the same as the Stokes equation that we did. So the derivatives goes from sigma to W. So you have grad W. W is already a vector. Gradient of W becomes a tensor. you're left with sigma without any gradient or divergence acting on it, which is a tensor. So you have two tensors, you want to get a scalar at the end, and that's the double dot product. That multiplies two tensors and gives you a scalar. And then you have the surface term where essentially it's the same sign, and the derivative, in this case, grad dot is multiplied, or divergence is multiplied by, is replaced by the normal vector. So just in place of gradient operator, you have the normal vector. So dot product between pressure plus viscous stress tensor with the normal vectors. That entire thing is the traction that we talked about. So it's a vector. Okay. And then you can leave your continuity term without any change. Some formulations also do integration by parts on the continuity equation. So if you want to do that, this is the form that this continuity equation becomes. So essentially, your gradient goes from the divergence acting on U to Q with a change in sign. Now Q is a scalar, grad Q is a vector. Two vectors dotted with each other gives you a scalar. For the boundary term, it's the same sign. Gradient is replaced with the normal vector. Okay. Now, if we assemble this into a matrix form, similar to the Stokes lecture, we have the exact same thing, basically, but the only difference is that we have now this additional term. So this highlighted term here, which is actually a nonlinear term. So I'm showing it with C as a function of U. So this is not multiplied by U. This is in parentheses U. So the matrix C, which represents it's a convection matrix. Unlike the advection diffusion equation, which C was linear matrix, now here it's nonlinear because U is the unknown. So and we have U dot grad U. So this is the matrix C, which is the nonlinear matrix. It's a function of U, the unknown of the problem. So we have to deal with it using different methods, such as the Newton method, or we'll talk about the simpler method at the end of this lecture on how to deal with this. So this system of equations, we have two challenges really, and these two challenges are really two challenges of doing CFD. Right? So the first challenge is that as the Reynolds number becomes larger and larger, this nonlinear term becomes more and more dominant. Your advection starts to dominate. And this U dot grad U term, this nonlinear term, which is really arguably the reason for all the difficulty in fluid mechanics and turbulence, this term becomes more and more difficult to deal with numerically using finite elements. So that's challenge number one. So challenge number one is instabilities induced due to high Reynolds number flows, which are because of this convection term. The second challenge is the coupled UP system that we talked about previously in the context of the Stokes equation, where because of these zeros that are here, or because really pressure doesn't appear in the conservation of mass part, but it's responsible for that. No, that was a physical interpretation. Because of this and the numerical issues associated with this zero, we're going to get some challenges related to pressure. So we have to be careful as we choose the space for velocity and pressures. And as I mentioned, the easiest approach, of course, if you can computationally afford the high cost, is to use a higher order approximation for pressure, for example, quadratic, and then lower order for velocity, for example, linear. So challenge number one manifests itself in oscillations in velocity. So if you look at your finite element simulation results, because of this first issue, you're going to see that your velocity is, it looks noisy, or you're getting oscillations, and then maybe even your simulation diverges as these oscillations, perturbations grow in velocity. Challenge number two shows up in pressure oscillations. So your pressure is going to get messed up, and it can ultimately cause blow up of your simulation. So now to resolve these two issues, for choice number one, the SUPG stabilization method needs to be used. Okay, so we have to use the SUPG stabilization for choice one. But as I'll talk about later, in the fractional steps method, it turns out that even without SUPG stabilization, for the fractional steps method, which we'll talk about in the next lecture, we can still get good result. We don't really need the SUPG stabilization in the context of fractional steps method. But when we're doing this coupled UP approach, where we're solving for velocity and pressure simultaneously like this, we do need SUPG stabilization, unless our Reynolds number is small enough and we can manage to have a very, very fine mesh. In solution number 2, so to solve the second problem, the coupled UP system and the pressure issue, we can either use a LBP condition. So for example, second order velocity, first order pressure. I might have said this opposite. So velocity has to be second order, pressure has to be first order. So that's, for example, if you're doing tetrahedral elements, you could do quadratic approximations. That's P2, P1, second order shape functions, or second order polynomial for your interpolating functions, shape functions for velocity, and first order for velocity. So velocity has to belong to a more accurate space. But that's often not available. So it might be difficult if you're implementing from scratch a finite element code. It will be very difficult. It's a time-consuming task developing quadratic shape functions in your code. So, but in FEniCS, if you're using FEniCS, then this is pretty easy. You just select 2 for your order of your shape functions. So if you cannot do this higher order velocity space, either because of implementation issues within your code or because you have the high computational cost, so second order simulation for velocity, that in a 3D mesh, that typically means like 8 times more degrees of freedom. So you're looking at like about an order magnitude more computational cost. So the second choice, which you can keep first order velocity, first order pressure, is to use pressure stabilization. Okay, and the pressure stabilization term is like this. So we have here the old big form that we had without stabilization that we just derived. And then we can add our 2 different stabilizations. We can have an SUPG stabilization, which looks very similar to the SUPG stabilization we had for the advection diffusion equation. We have the residual of Navier-Stokes here. We have U dot grad acting on W, and then you have this tau, this stabilization parameter. And then you also can use a pressure stabilization. So if you choose not to use second order velocity, first order pressure, then you can instead add a pressure stabilization to overcome these second issues. Okay. So in this case, again, it's proportional to the residual, and then you have gradient of Q, the test function for pressure, dotted with tau over. And tau here is a stabilization parameter. It kind of looks like the choices we've had for the advection diffusion equation. It depends on the mesh edge size and among other things. And there are different choices for tau. If you like to see some details about this, I encourage you to read this very good recent paper that talks about these and actually proposes a more consistent and newer way of defining these parameters. So I will provide a link to this great paper in the description box below, where you can learn more about how to select this parameter tau for CFD simulations using the coupled UP approach. Okay, so now the other thing we need to deal with here is the nonlinearity. Of course, this is no longer really a linear system of equation, because this part here also depends on U. So that makes this nonlinear. And we all know fluid flow, they're nonlinear because of this advection term. So how do we deal with that? There's the more robust approach using the Newton method, which we'll talk about later. But there's a very simple approach known as the Picard iteration method, which I'll explain here, which is very, very simple. And this is actually the simplest method that you can use to treat the nonlinear term. So imagine, so here you're iterating. For example, you start with an initial guess U0, and you keep iterating until you converge the solution. And as you're solving the Navier-Stokes equation using a finite element formulation, for the convection term U dot grad U, this convecting part, this U here that's multiplied by grad U, you evaluate at the previous time step. So you evaluate this part at the previous time step. So, and that's, or at the previous iteration, if you're doing iterative method for a steady solution, this is evaluated at the previous time step, which you know. So if you do that, if you make this lag, basically like you approximate this, you lag this velocity behind, basically either back to the previous time step or previous iteration step, then this becomes linear. Okay, this becomes linear because now your unknown is only UN. So this becomes kind of like similar to advection term for a mass transfer problem, which is also linear, right? Which what we talked about previously. So here UN minus one is known from your previous iteration, and you solve for UN, and you can iterate on this until you reach convergence. Okay, so this is the simplest method for dealing with a nonlinear term. It's very easy to implement, but the issue is that it's only first order, and you might need more iterations. So for the Newton method that we shall talk about later, that can often converge within a few iterations. So it might be faster in terms of iterations than Newton method, even though it has more operations or more calculations within it. And another thing that you might say is that why don't we also make this one n-1? So you can also, if you made both of them belong to the previous iteration, so here you also had n-1, then this entire term will be known. It becomes just like a source term. So your equation is really like a Stokes equation with the source term, right? So that method, it turns out that one, that's actually obviously the easiest, but that one only works if your Reynolds number is relatively low. Okay, so, but this Picard approach, tends to work better. But again, Newton's method is often preferred, which we'll talk about that later.